All right, last class, we wrapped up, we went over a bunch of the different changes in phase, and we very quickly went through this heating curve. So there's a couple of different important features of this graph. Anytime that you see temperature changing over time, which is what we have on our x-axis, anytime temperature is going up, that means that we only have one phase of matter. And what we're looking at here is heating up ice, because ice as a solid water can be very, very cold. It can come up all the way to 0 degrees Celsius under normal conditions. And then we get a flat line here. We're putting in temperature. This is essentially time that we've got water on a burner on the stove. While the ice is melting, the temperature is locked in at 0 degrees Celsius. It's locked in at the freezing point. We've got both water as a liquid and water as a solid in this melting ice phase. Once it's all completely melted, then we can get into heating up our liquid water. Once that gets to its boiling point, then all the energy is going into vaporizing the water, turning it into a gas, boiling off the water. Once it's all boiled off, then the steam can start to heat up. We talked about some changes in temperature stuff related to that, some energy exchange last time. We're finally getting into solutions. So a solution is a homogeneous mixture. That means that it's one smooth, consistent layer of two or more substances. They can be the same type of substance, they can be compounds, they can be different elements, just two or more substances. Solutions are super common. They're all over the place. So again, solution is a homogeneous mixture, smooth, consistent mixture of two or more substances. There's a lot of different types of solutions. So all that we're looking at here on the graph, all that I'm trying to show you is that we can have lots of different, what's called a solvent phase and solute phases. So we can have lots of different combinations. Usually what we think of is a solid dissolved into a liquid. But there are lots and lots of other examples of things that are solutions. Solids dissolved in solids, liquids dissolved in liquids, gases dissolved in gases. A solution is always going to have at least two components. Those two components are the solvent and the solute. So the solvent is the majority component. You maybe have heard about solvents. You've maybe heard people say solvents. I think typically I would hear it if you're talking to like mechanic type people. They might use solvents to wash off like auto parts. If you get oil or grease on an engine part that's made of a rustable iron, they're going to wash it off with something like hexane or some other non-polar solute, or solvent rather, so that they're not rusting their parts. That's where I would imagine we might have heard of solvents. So solvent, the majority component, what there's more of. Solute is the minority component. Oftentimes, when we're thinking of solutions, the solutions that we think of, a solid dissolved into a liquid, the solid is called the solute, and liquid is called the solvent, regardless of whether that's technically true. So even if we have more of the solid than we have of the liquid, somehow, we would still refer to the solid as the solute, and the liquid is going to be the solvent. We usually think of solvents as liquids. The most common solutions have water as their solvent. If water is the solvent, it's an aqueous solution. So water is the solvent. Water does the dissolving. It causes the other things to dissolve. There are other solvents used, especially if you have non-polar solutes. Our rule for what things will dissolve what other things is very general. It's like dissolves like. And what this means is that polar solvents dissolve polar solutes. So we'd use a polar liquid to dissolve a polar solid. and nonpolar solvents dissolve nonpolar solutes. This is helpful if you know about polarity. We learned about polarity. The more experience you get as a chemist, the more chemistry you take, the faster you'll be able to identify things as polar or nonpolar, and the more helpful this like dissolves like will be. Common solvents that are polar include water, acetone like in nail polish remover, methyl alcohol, wood grain alcohol. Some common nonpolar solvents, hexane, diethyl ether, toluene. We'll have hexane out today in the lab, so if you want to smell it, it just smells like gasoline, essentially. And here's how dissolving things works. When you drop something like sodium chloride into water, here's our water on top, there's competition. When you have salt by itself, the sodium ions and the chloride ions are attracted to each other. They're in this matrix that exists of repeating positive, negative charges, 3 dimensions, as far as you can imagine. In water, it's just all the water molecules floating around, touchingly close, interacting with each other. When you drop the salt in, now there's a competitive force between the water and the sodium ion and the water and the chloride ion. If the force between the water and the sodium or the water and the chloride is stronger, it will pull apart the sodium chloride ions. If the sodium and the chloride attraction is stronger, it will not dissolve. So not all ionic compounds are soluble in water. For example, calcium carbonate, the calcium and carbonate ions are more attracted to each other than water is attracted to them, and so they don't dissolve. When they do dissolve, like sodium chloride table salt, how the ions actually exist is like Buzz Lightyear and the claw machine in Toy Story. At Pizza Planet, the claw. Like all of the LGMs, the little green men, like with their arms reached out to Buzz Lightyear. That's what I imagine this is like. It's maybe a little bit of an older reference for some of us. But the way that this exists, the sodium ions are in the middle of a bunch of different water molecules, and the water molecules have the oxygen side, that's the partially negative side, pointing towards the sodium ion. The chloride ion, on the other hand, has the partial positive sides of the water molecules pointing towards it. This is to stabilize the charges. This is also how they get pulled apart. A bunch of the water molecules come along, they latch on, and then through random motion, they get pulled away by the other water molecules, or they move away by the other water molecules, and that pulls apart the lattice of the sodium chloride ions. Usually we omit the water part. So if you put salt in water, it separates out, and we're not drawing in all of the little water molecules with the positive or negative ends on the ions. In a sodium chloride solution, so a mixture of sodium chloride in water, sodium chloride aqueous does not contain any NaCl units. There's sodium ions, there's chloride ions, there's no NaCl in NaCl-AQ. They've all been entirely, completely separated. It completely dissolved into ions. Ions conduct electricity. This is a strong electrolyte solution. If you've been around anything related to fitness, you've probably heard about electrolytes, right? We drink sports drinks to replenish our electrolytes after we've gone on a long run, we've had a long day out in the sun. The electrolytes are essentially salts that our body needs to continue functioning, which you probably have learned about if you've taken some biology. Because the sodium chloride completely dissolves into ions, the completely dissolved parts means that it's strong. Completely dissolves if it's strong, and because it dissolves into ions, that's what makes it a strong electrolyte. So the ions part is referring to the electrolytes. This brings us into our fourth force. We had talked about three forces previously. We had the London dispersion force or dispersion force. That's the electrons randomly being on one side or the other. Everything that has electrons has the dispersion force. So one was our dispersion force. Everything has that. This is just a little review. We also had dipole-dipole forces. Dipole-dipole force was between the dipole of one molecule and the dipole of another molecule. And polar molecules have dipoles. So polar molecules can have dipole-dipole forces. We also had hydrogen bonding, which was like our super dipole-dipole force. Things that have hydrogen directly bonded to fluorine, oxygen, or nitrogen can do hydrogen bonding. It's that intermolecular force like between the base pairs in DNA. And then our fourth force is the ion-dipole force. And part of the reason that I point out for the dipole-dipole force that it's between one dipole and another dipole, because our ion-dipole force is between an ion and a dipole. Our ion being a charged particle, so something with full positive or negative charges. And the dipole being the partial positive or partial negative end of a polar molecule. So the ion-dipole force can occur in mixtures of ionic compounds, things that form ions. That's the ion part of the ion-dipole force. And polar compounds that have dipoles on them, permanent partial positive, partial negative charges. This is very important for aqueous solutions of ionic compounds. For example, our example from earlier, sodium chloride dissolved in water. So this is what the ion-dipole force looks like. Because we've swapped out one of these dipoles from the dipole-dipole force with an ion that's a much bigger charge, we've essentially got a really big strong magnet with a little small, not as strong magnet. This is going to be a stronger force because of the ion that's involved. You may know, you may not have known, that ions conduct electricity. I mentioned it earlier. Pure water does not conduct electricity, or at least not very well. So in theory, you could take a bath in completely pure water. If you were completely clean and you didn't leach ions into the water, you could take a bath in pure water and safely make toast in the bathtub. Because if it fell in, it wouldn't conduct electricity, so you wouldn't have a very big surprise if it fell in. It would just be wet, and that would be bad. Ions in a sodium chloride solution conduct electricity. Our water has lots of ions in it because we've got hard water. Soft water also has ions. It's usually just different ions. So things like KCl have high conductivity because KCl, potassium chloride, is a strong electrolyte solution. So this has high conductivity. So if you were to drop a toaster in, it would conduct electricity. That'd be a big surprise. Or in the case that we've got here, you can light up a light bulb by passing the electric current completing the circuit through the solution. If you've got something like acetic acid, it's got less ions in solution, and so it's a dimmer bulb. If you put something in that's made of molecules, like ethanol, molecules don't form ions when they dissolve generally. Acids are an exception, but ethanol would be an example of something that doesn't form ions, and so the light bulb doesn't light up, it doesn't complete the circuit. There's no ions to run electric charge back and forth between the plates that we've put in the water. So electrolyte solutions contain dissolved particles. Electrolytes are ions. Non-electrolyte solutions contain dissolved molecules. So dissolved neutral particles sugar, ethanol. There's lots and lots of other examples of things that are dissolved neutral particles. But any molecular compound that's not an acid, not a strong acid at least, would be a non-electrolyte solution. So electrolytes are ions, sports drinks full of ions. Dissolved neutral particles like sugar are non-electrolyte solutions. They don't have ions in them. Electrolytes equals ions. Example of some electrolyte solutions. A silver nitrate solution, if you put it into water, AgNO3, doesn't contain any AgNO3 units because it's a strong electrolyte solution. So it completely separates into its ion parts. When compounds containing polyatomic ions dissolve, unless it's a gas evolution reaction, the polyatomic ions dissolve as intact units and they stay as intact units. So something like NO3 minus would stay as NO3 minus units. We just separate it into its positive and its negative. So ionic compounds that dissolve into cations and anions are positive and negative charges. Ions. Things that don't dissolve, of course, are not going to do that because they don't dissolve. So AgNO3 is something that does dissolve. AgCl, silver chloride, does not dissolve. So not all ionic compounds dissolve in water. We're mentioning it again because it's important. AgCl remains a solid, AgCl, silver chloride, when it's put into liquid water. It does not dissolve into independent ions. So we're showing the water molecules on the outside having no effect on our silver chloride. It'll just stay in there as a clump. It's not going to go into solution. So our aqueous solutions are homogeneous mixtures. The solutions part means that it's a homogeneous mixture of a substance. The aqueous part is referring to the water. Aqueous is water, the solution part, homogeneous mixture of a substance. When something dissolves, it still exists. And has mass. It also still takes up volume. This is something that you could experience for yourself if you wanted to, if you're making some salt water, or if you just have some extra salt lying around. Take a glass and fill it up a certain amount. Mark off where it fills up to, add a bunch of salt in there, get all the salt to dissolve. You'll notice the line went up because those salt ions, even though they're ions, still take up space, and so your volume is still going to go up. And we can talk about solubility. In this class, we are going to be using qualitative rules of solubility, which is good for us. If you take Chem 2, you will be doing quantitative solubility, which involves a lot of math. So that's why I'm saying it's good for us that we're doing qualitative rather than quantitative. Things are soluble if they will dissolve. Soluble means it will dissolve. It does dissolve. It will dissolves. Insoluble means it does not dissolve. The in prefix here meaning not. So for example, AgNO3 is soluble in water. That was our first example. from a couple slides ago. AgCl, silver chloride, is insoluble in water. It stays intact as its complete formula units, as a clump, when you put it into water. We have empirical rules of solubility that you do not need to memorize. There's a table for it, so we're going to walk you through how to use the table. You have one of these tables on your green sheet, the side of the green sheet that we haven't really touched at all. You've got a solubility table there. We're also going to look at one from our online textbook. This one is slightly different from the one that we've got on our green sheet. I think I usually give you the green sheet one on exams, but I don't remember for sure. You'll get a solubility table if you need it. So the way that we read a solubility table, this top section is things that are soluble. So we're looking at the first column on the left first, things that are soluble in water. And we would be looking for anything that's in the compound that we have. If we find it here, that means that it will be soluble in water. We also have to check if there are exceptions, because there's often exceptions. So for example, if we've got something that's got ammonium in it, like ammonium chloride, NH4Cl, the NH4 part is the ammonium, so we would find NH4+. It's soluble in water. There are no exceptions, so that means that this is soluble. If we pick something from the bottom group, something that's a carbonate, a CO3 2-, something that has a phosphate, PO4 3-, sulfides, oxalates, hydroxides, any of these things, and we have an exception, then it will be soluble. We'll do examples, so I'm not going to beat our brains on that for too long. So our solubility rules, again, these are a qualitative description. It's not going to tell us how much will dissolve or how little will dissolve. It just says, yes, it dissolves, or no, it doesn't dissolve. So we want to read through our table and figure out whether each of these compounds is soluble or insoluble. We already did NH4Cl. That one is soluble because ammonium shows up in the soluble table, the soluble side. For CAS, if we're using the one from the book, we need to know what CAS is. It's calcium sulfide. Calcium's probably not going to be on there, but sulfide is. So we've got sulfides in the sparingly soluble. For us, this means insoluble. It doesn't dissolve. Okay, so sulfides are not soluble in water, so not soluble, but we do have an exception for CAS, so it is soluble. So it's not soluble, but there's an exception, so it is. I'm writing it out this way to try to help you work through the process in case you come back and look at the slides. So this one is soluble. We've also got FeSO4. SO4 is a sulfate. We have sulfates in the soluble in water section. So sulfates, our initial read is that it's soluble, and we have to check for exceptions. So we look over at the right column. Do we have any important exceptions that are insoluble? I don't see FeSO4 there. So we don't have an exception. That means it is soluble. And we also have PbCO3. CO3 is carbonate. We've got carbonates in the sparingly soluble part of our table. And do we have an exception for lead? We've got an exception for group 1A, which is our alkali metals. That's the far left column of the periodic table. We've got an exception for ammonium salts. That's because those are always soluble. We don't have either of those. We've got lead instead. So this is insoluble because it's on the insoluble part of the table and there's no exception. Sometimes you can find both of the ions. A lot of the time, though, you can only find one of the ions in the solubility table. You just have to check if there's an exception for the other ion. Questions about using this table? Again, I think in the past I've given you the one on the green sheet that has the chemicals, like their symbols, instead of the names. So it's a little bit easier. You don't have to be cracked at nomenclature just to be able to read your solubility table. Part of the reason that solubility is important is so that we can do precipitation reactions, a new class of reactions. We've seen precipitation reactions before, but we haven't covered them in lecture yet. So sodium carbonate that's in laundry detergent reacts with dissolved magnesium and calcium ions. Those form solids that precipitate from the solution. So in your washing machine, you throw in laundry detergent. Usually it's got some compounds in there that pull out hard water ions from the water. Hard water ions typically interfere with the ability of your laundry detergent or other soaps to do their soap action. So if you've got really hard water at home, like especially if you're on well water, but our regular tap supply is also pretty hard. When you go to wash your hair, you're going to get less of a lather around here because your hair products probably don't have hard water detergent qualities to them. They're not pulling out hard water. If you go to somewhere like the Bay Area where they've got soft water and you wash your hair, you're going to be like, oh my God, I'm getting so much lather from this soap. What's going on? It's the qualities of the water that are different. And so the way that laundry detergent counteracts having hard water is that it's got some compounds that pull out those ions that lets your detergent, the soap, actually do its job better. And these are examples of precipitation reactions. Precipitation reactions, our definition, the one that I'd like you to learn at least. A solid forms, the solid is the precipitate, upon / after / from mixing two aqueous solutions. So the important parts here, they're aqueous solutions. That means the ions are completely dissolved. We don't already have solids in there. Completely dissolved ions. We mix the two solutions together, and there's a love at first sight reaction between those ions that we've added into solution. And so they find each other in this new mixture, and they crash out, which just means that they form a solid, and they come out of solution. So a solid forming from mixing aqueous solutions. That's our precipitation reaction. An example of this is when you mix potassium iodide solution with lead 2 nitrate. You get this bright yellow lead 2 iodide solution, or precipitate rather. You don't always get precipitation reactions when you mix two aqueous solutions, so sometimes you mix two things together and they're still soluble, and now you've just got more ions, but in one solution. Like is happening here, where you just have bubbles from them mixing these two things. There's no solids coming out of solution. So the key to predicting precipitation reactions, which are typically double displacement reactions, is understanding that only insoluble compounds form precipitates. So check our possible products to see if any are insoluble. And we'll be doing some examples of this. By the way, I am intentionally going fast because we have so much lecture material to get through. So I'm trying to be a little bit more brief about what we're talking about. All right, when we mix potassium iodide and lead-2 nitrate, before mixing, we've got lead iodide dissolved in solution. We've got lead-2 nitrate dissolved in solution. Only ions in solution. It's completely dissolved. Completely dissolved solution, completely dissolved solution. After we mix them together, what possible combinations of ions can we have? There are 4 ways that we can combine our ions to form ionic compounds. What's one of the combinations? Somebody pick a positive ion and a negative ion. Our options are K+, Pb2+, I-, NO3-. Somebody pick a positive and a negative. Potassium and what else? Potassium and iodide. That's one possible combination. That would have the formula Ki. So that's one possible combination. What's another possible combination? Potassium could go with the NO3, K+, and NO3-. Those are both one positive, one negative. So those will balance out perfectly, 1 to 1. What's our other 2 options? We can have the lead and the iodide. That would make PbI2. That's another option. We could also have the lead with the nitrate, which would give us PbNO3 2. So we've got 4 possible options, 4 possible mixtures of ions that we could get up to in this solution. 2 of these we do not need to check because we saw them before mixed up, right? We had Ki, aqueous. That means it's completely dissolved. It's soluble. PbNO3 is also soluble, so we don't need to check these if we're looking for whether a precipitation reaction occurs. So Ki, PbNO3, these are aqueous reactants, so we know that they're soluble. We don't need to check them. The 2 that we didn't check, or that we need to check, are the KNO3 and the PbI2. Those are the 2 new combinations of ions. So we took our positive ions, our negative ions, and we swapped one of them. We swapped our negative ions. As it turns out, the PbI2 precipitates, the potassium and the nitrate ions stay in solution. And this is what potassium or lead-2 iodide looks like. The colors are because they're that element. When we're writing equations for precipitation reactions, it's basically the same as double displacement reactions, which we talked about a while ago. So we want to write the formulas of the 2 compounds being mixed as reactants. So we'll write those on the left side. Below the equation, separate the reactants into their component ions. They have to have their charges with them. Then we are going to swap. I usually swap the negative ions. rewrite on the product side. And then we'll do our swap and drop to get the neutral formula unit. We'll also check solubility. If you want to, you can check solubility before you do any of this. If you just, in your mind, pick the positively charged ion from one thing, the negatively charged ion from the other thing, you find those on the solubility table. If they're soluble, move on to the next one. If it's insoluble, write it out, we've got a reaction. Check the other one. So you don't have to do, technically you don't have to do any of this before you figure out if it actually produces something, which could be a time save. Alternatively, you can just do these steps every single time, and then you don't have to worry about possibly screwing up, mixing up something. If both pairs are soluble, you would write no reaction next to the arrow. So let's say that we've got a generic equation, AB plus CD. They're both soluble. We would just write no reaction, like that. Goes to, no reaction. Nothing happens. We just combine them together, nothing fun. If one or both of the new ion pairs is insoluble, the insoluble compound is S. It's a solid. Soluble is AQ, aqueous. The last step would be to balance the equation by adding coefficients, numbers in front of our compounds. We're not changing any subscripts. And to balance the coefficients, typically we're going to be using the method. You find one thing that's unbalanced on both sides, balance it. What was the other thing that you changed when you did that? Balance that. What was the other thing that changed when you did that? Balance that thing. Let's look at some examples. We want to predict what will happen if aqueous solutions, this is important, aqueous solutions, they're dissolved, of rubidium hydroxide and cobalt-2 chloride are mixed. Notice that we're given chemical names, not chemical formulas. That means that we have to be able to do nomenclature, at least for this type of problem. So rubidium hydroxide and cobalt-2 chloride are our chemicals. Rubidium hydroxide is Rb plus and OH minus mixed together. We've got 1 plus, 1 minus, so those two go together in a 1-to-1 ratio, RbOH. It's aqueous. Cobalt-2 chloride, what does the 2 in cobalt-2 chloride mean? It means that it has a 2 positive charge. Doesn't mean we have 2 of them, it means we have a 2 positive charge. It's the charge of the metal, it's a transition metal. So we've got CO, 2 plus, CO is our symbol for cobalt, and we've got Cl minus for chloride. We need to swap and drop this. When we combine it, it's going to be COCl with a subscript of 2 to let us know there are 2 chlorides there. If you've completely forgotten nomenclature, putting together ionic compounds, balancing equations, Logan would love to drill those with you in the steam room, 1 to 3. So these are our 2 reactants. And the reason that I wrote out the ions below is because if we started with the formulas, we would be splitting them into their ions before we swap. So I started below so that they're already split up. Now the swap part. We're going to swap hydroxide and chloride and then rewrite them on the other side. So we've got Rb plus now with Cl minus. We've got CO2 plus now with OH minus. And we can combine these into RbCl and COOH2. We don't know if they're soluble. Enter green sheet, solubility table. Looking at RbCl. On the solubility table in the top section, the third line entry for our green sheet, Cl minus, Br minus, I minus is in the soluble section, except for those containing silver, a species of mercury, and lead 2+. Do we have any of those exceptions here? Do we have silver, mercury, or lead? No. We've got rubidium. This is aqueous. It's soluble. Our rubidium would also count as soluble because that's a group 1 metal. Those are also soluble. So we have to look at our other chemical, COOH2. We can find on our green sheet table, hydroxide is all the way at the very bottom. This bottom section is our insoluble section. So OH minus being down there, we have to look and see if there's any exceptions. So OH minus, hydroxide is generally insoluble, except for group 1 and ammonium, NH4+. We've got cobalt 2+, which is neither group 1 nor ammonium. It's slightly soluble when it's paired with calcium, strontium, and barium. Cobalt is none of those. So it's generally insoluble, not soluble, and we don't have an exception. That means it's not soluble. So we've got ourselves a reaction. Are we done? Not quite. We still need to balance. So we need to look at what's something that's not the same on the left as it is on the right. A chemical that we have more on the left than on the right, or more on the right than on the left. What's something that's not balanced? Chlorine. So for our Cl, we've got 2 on the left, we've got 1 on the right. We need to bump those numbers up on the product side. So we're going to double it, add a 2 in front of the coefficient. Now chloride's balanced. What did we change when we balanced the chloride? We changed the rubidium, so we're going to balance rubidium next. So looking at Rb, we've got 2 on the right because of that coefficient of 2. We only have 1 on the left. Got to bump those numbers up. So we add a 2 in front of RbOH on the left side. When we balance the rubidium, what else changed? The hydroxide is the other thing that changed. We had 2 on the left side, so for our OH, 2 on the left side, and lucky for us, we've got 2 on the right side. That typically means that we're done once you get to something that's already balanced, but let's go ahead and check our last thing just in case. So we've got cobalt, 1 on the right, 1 on the left. We are now balanced, so we're done. Any questions about precipitation reactions so far? So again, our general definition for precipitation reactions. Precipitation, another place that we've heard of precipitation, maybe the only other place we've heard of precipitation is relating to weather. Rain, snow, sleet, hail, things coming out from seemingly nowhere. That's what's happening in precipitation reactions. You mix two aqueous solutions together, two dissolved solutions together, and boom, out of nowhere, now you've got a probably white powder floating around on the bottom of your solutions. The precipitate is the solid. We're going to skip all the other examples. If you want to see them, I'm almost 100% sure that I went over them last semester. You can find the old lecture recordings from the fall 2025 playlist for Chem 20. So that's one of the chemical equations that we can write. There are actually a couple of types of chemical equations. So we've always been looking at the molecular equation. What we've been using is the molecular equation. The molecular equation shows neutral formulas, or molecules, for every compound in the reaction. This is also sometimes called a complete chemical equation. We also have complete ionic equations. This shows all ions as ions. So when we're converting to a complete ionic equation, anything that's AQ we're turning into ions. That's how we get from our molecular equation to our complete ionic equation. If it's a solid, liquid, or a gas, that's not ions. It stays as a solid, liquid, or a gas. So in this example, our cobalt-2 hydroxide is a solid. That stays as COOH2. All of the other three things we would separate out into their ions. So it would be Rb plus, OH minus, CO2 plus, Cl minus, with the necessary coefficients. So we'd have 2's in front of the rubidium and the hydroxide. We'd have a 2 in front of the chloride. On the product side, 2 in front of the rubidium and the chloride, because this 2 distributes. And then COOH2 stays as COOH2. So separating all of our ions into their ions if they're AQ. We also have spectator ions. What do spectators do? Watch. They're the fans at sports games. They just watch, they don't participate. They're not actually involved in the what's going on. And that's the same for our spectator ions. Spectator ions don't participate in the reaction. They'll look the same on the left side as they look on the right side when we're looking at our complete ionic equation. So if you find something that's the same on the left and the right, that's a spectator ion. And we can omit spectator ions, and when we do that, we get our net ionic equation. Not complete, our net ionic equation. If you work a job, if you've ever worked a job, you probably have some experience with net versus gross. Your gross pay or your complete pay, that's the amount that you're actually getting paid. Your net pay, that's the amount that you actually get to keep. This is once all the taxes and fees and stuff have been taken out. Your net ionic equation is the same idea. We've taken some stuff out. So the net ionic equation removes or omits the spectator ions. No spectator ions in the net ionic equation. So our summary of our equation types. The molecular equation, that's what we've been doing, shows our complete and neutral formulas. Our complete ionic equation, emphasis on the ionic part, shows all of the species, all of the chemicals as they actually are present in the solution. So this separates AQ species chemicals into ions. And then our net ionic equation removes spectator ions. So it's going to include whatever our product or products are and the ions that go into them. And that's it, just those things. Let's look at an example. Consider this reaction occurring in aqueous solution. Write a complete ionic equation and a net ionic equation for the reaction. Are we going to, when we're writing the complete ionic equation, are we going to separate BaCl2? Does that one get split up into ions? Yes or no? Yes. Yes, it does. Why does it get split up into ions? It's got the AQ symbol. The AQ means aqueous. That means it's dissolved. It's an ionic compound, so that means it's dissolved as ions. Are we going to split up Na2SO4? Also, yes. Why? It's AQ. That means that it's dissolved as ions. Are we going to split up our BaSO4? No, why not? It's a solid, so it actually exists as BaSO4. It's clumped up at the bottom. So that's going to stay as BaSO4. And then what about NaCl? Do we separate that one into ions? We sure do, again, because that's AQ. So splitting them up into their ions might require us to do a little bit of math. Not math, math. So BaCl2, what's the charge on the barium? It's a 2+. Barium shows up in our alkaline earth metals. It's our second column. So it gets a 2+ charge. If it was in our first column, it would get a 1+ charge. But it's in the second one, 2+ charge. So barium, 2+. We could also figure that out because we've got chloride. Chloride is one of our halogens. It's one spot to the left, the halogens, one spot to the left from our noble gases. Noble gases are no charge. Halogens, 1- charge. Things under oxygen, chalcogens, 2- charge. One more over, 3- charge, in case we've forgotten our ions. So we could also figure it out based on that. We've got 2 and they're a 1 negative charge. So Ba, 2+. If we want to be really robust, we include the little AQ. I'm going to omit the AQ. We'll just assume that it's AQ. How many chlorides are we going to have? 2. We've got a subscript of 2. So we've got 2 Cl-. Moving on to our Na2SO4, we've got a subscript of 2 on the Na on our sodium. So we've also got 2 sodium ions. Sodium's a 1+ because it's in that alkaline or alkali metal column, the first column. And we've also got our sulfate, SO4. What charge does SO4 have? 2 negative because we either memorized it or we look at, we've got 1 positive charges for the sodium. That has to balance out with our sulfate, so it must be a 2 negative. So SO4, 2-. This is going to BaSO4. BaSO4 is a solid, so it gets to stay as BaSO4. I'm going to write the solid there so it shows why we are keeping it. And then we've got our NaCl. We've got a 2 in front of that. in our balanced chemical molecular equation. So that 2 distributes to our sodium and our chloride. It's the same ones that we had on the left side. So 2 Na plus and 2 Cl minus. So this is our complete ionic equation. What do we do to get to our net ionic equation? What are we removing? We're removing our spectators, which are the ones that didn't participate. So now we get to play a spot the differences game with our chemical equation. What's the same on the left side as it is on the right side? We've got Na plus. What's our other thing that's the same on the left and the right? The chloride. Chloride stays as chloride. The barium and the sulfate combined to form the solid on the product side. So those ones did change. They did participate in the reaction. So we're going to remove the ones that are underlined. That's the Cl minus and the Na plus, because they're spectator ions. So our net ionic equation, Ba2 plus SO4 2 minus goes to BaSO4 solid. Questions about our fourth force, the ion-dipole force, polarity and how it affects dissolving things, solvents, solutes, complete ionic equations, net ionic equations, molecular equations. Cool, then that'll do it. We finished the chapter. We'll start a new one on Tuesday.